All right, this is it. This is kind of the culmination. We're going to put a whole bunch of stuff together to answer this question. We have one more topic to learn before we're done the unit, but it's just a small topic. Really, this example number 9, if you can figure out how these pieces fit together, uh, super important for this topic. I'm going to doodle it. I didn't give directions in the question, so I'm not worried about directions. I'm just going to doodle it out so you have an idea of what's happening. But we've got a parallel plate connected to a 30-volt source. Electrons are added in between the plate. They get drawn, they get attracted towards a positive plate and end up zipping through a hole. They end up over here going at some speed v. After that, they enter a magnetic field. I'm going to draw the magnetic field as x's. It doesn't say in the question, it just says that they enter perpendicular to it. They enter as x's. When the electron gets to that magnetic field, we'd have to do our left-hand rule, high five hand, left thumb pointing to the right, fingers matching x's, so away from you. Your palm should be facing the floor. What that means is when this electron gets here, it's going to have a force on it that pushes it towards the floor. That's going to bend it in a circular path. As the force bends the velocity vector, that changes the direction of the force as well. So when that electron enters that magnetic field, it's going to follow a perfect portion of a circle. How much of a circle depends on how fast it's going and how big the field is. Maybe it'll do a perfect half circle and leave again, or maybe a quarter. But it's going to follow circular motion when it's in the magnetic field. There's enough in this question that we can figure out the radius of that circle. By the time we get to the unit wrap up, you should be comfortable with this style of question, how voltage connects to speed, how speed connects to centripetal, to force, to the circle. I could ask you in any direction. Maybe I could give you the radius and have you backtrack and figure out the voltage or something like that. You don't need to memorize numbers, but as we're using this, the mass of the electron is 9.11 times 10 to the negative 31 when we're in kilograms, and the charge on electron is 1.6 times 10 to the negative 19. For this first one, I'm not worried about the directions. I just thought of that because a charge of a negative, all that negative would do is when I got to the left-hand, right-hand rule, help me with the directions. So I'm not even going to put the negative in when I do the math for this. All right, here we go. For this particular setup, we need to know how fast it's going. How fast it's going, in disguise, we're told that when we were told the voltage. So in the plate, shooting an electron is a conservation of energy thing. The electric field energy gets converted to kinetic. Electric field energy is always Q times volts. Kinetic is always 1/2 mv squared. There's enough there that we can figure out the speed of the electron. Its Q was 1.6 times 10 to the negative 19. I'm not going to put in the negative. If I did, I'd have to put a negative with the 30 as well, because the 30 volts did positive work on a negative particle. So they're either both negative or both positive. Equals 1/2. The mass of the electron is a 9.11 number times v squared. Doing the math on that, we could rearrange to get an expression, but this time I think I'll get a number, however you want to do it. If you do get this partway number, it's 3.25 times 10 to the 6 in meters per second. That's the first part. Then, once that particle is flying at 3.25 times 10 to the 6, it enters a magnetic field. The magnetic field, because it's a charged particle, is going to put a force on it. That turns into that cool stuff we did, that new stuff we did this year, last unit. F net equals ma. The only force acting on it is the electric force. Its equation is QVB sine the angle. That bends it in a circle. So just like we did for other centripetal things, satellites, rocks on strings, cars on corners, we replace the A with V squared over R. We can clean it up a little bit. One of the V's will cancel. So this V cancels with this V. In this particular arrangement of the question, I'm curious about the radius. When I flip-flop things around, radius is mv over qb. So for this one, the mass is 9.11 times 10 to the negative 31. The speed we figured out was that 3.25 number. It's an electron, so I know the Q value is 1.6 times 10 to the negative 19, and the B value I made up for this one was 0.5, which is a pretty strong magnetic field. If we set it up that way, the radius, you can double check my math. I'm getting a number approximately 3.7 times 10 to the negative 5 meters. Comes across as kind of a small number, but if you think about the scale of an electron, that's huge compared to the size of an electron. As I was saying earlier at the start of this is an important question, kind of a culminating type question. The only way to do this is to understand all the little concepts. You need to understand the conservation of energy for accelerating the charge. You need to understand that there's a force on it, and that the force triggers the centripetal motion that we covered in Unit 1. You should be able to do this question forwards and backwards. If I give you the radius and the B value, you should be able to work backwards and figure out the speed, and from the speed work backwards and figure out the voltage. So I know there's some on the worksheet, but go over a couple of these, make sure you're